This is the 2025 meeting. If if anybody wants to raise their hand or unmute for a second, if you bought any equipment or you're a new member and you want to introduce yourself, feel free to do so. Otherwise, I'm going to keep going. Any new members on the group? Okay. So I'm gonna do this one really, really quick. Since we're not in the building, I do want everybody to be safe. So we're all remote attendees, so please be aware of your surroundings. Don't trip on your cat or something, that kind of thing. So, upcoming events for everybody, just to talk about this. Sanderson High School. Is Steve on the phone? On the phone. On the Zoom.
Dana, Tony is here. I did the event at Sanderson High School.
Sweet. How did it go? Well, that says upcoming.
No. Well,
we got two of them in there. Oh, well, sorry.
Yeah, it was past a couple of Mondays ago. It went very well.
Okay. And first, that's good, Tony. I think I saw a picture of that. So June 6th, I know got canceled. Did it not?
Yeah, it was
First
canceled.
Fridays. Okay. We got the Willard coming up. We got second Saturday on my birthday. And we got stargazing on tap on the 26th in Cameron. So I like that event. All right, Tony. Tony Rice is a longtime volunteer with the NASA JPL Solar System Ambassadors Program, and he's a science contributor to WRAL TV. I see him on TV once in a while. When not supporting the meteorologists around the country with astronomy information, he visits NASA and NOAA facilities to get the latest information about missions and programs to share. Tonight, he's going to talk to us about space weather predictions. Tony, I hand it over to you.
Thank you, sir. Let me share my screen. Yeah, as I mentioned before, I'm not going to bother with boring you with slides. I think we all see enough of those the rest of the week. So let's look at something kind of cool. So wasn't last week, it was the week before last, I was out in Boulder, Colorado on business and scheduled my flight back to Raleigh pretty late so that I could get up on my travel day and head over to the campus there at the base of the Flatirons. I mean, you walk outside of the NOAA offices, you walk outside of the NIST offices there, and it's amazing. You're looking up at the Flatiron Mountains there. It's absolutely gorgeous. And that's what those folks see every day when they walk out. But I spent the morning with the folks at the Space Weather Prediction Center. We'll talk a lot about that today. And also got the chance to visit with some folks about 300 yards across campus at the National Institute of of Standards and Technology, NIST, and got to talk with, just happenstance. I'm walking out, I'm running a little late, heading towards Denver to the airport and not miss my flight. And who should walk in but a gentleman who is about 2 weeks away from retiring. And he is the person who is responsible for the UTC time standard here in the United States. They call him Father Time there. They call him the Time Lord. He's not sure which one he hates worse, because he says it's a team effort there, and he really hates all the attention. But I spent the flight back reading some of his papers. He's responsible for a lot of the time standards we have, which you get deep enough into the data of astronomy and you'll realize how important time is. So I got to see a couple of atomic clocks while I was there, a decommissioned one that's sitting there in the lobby in pieces, as well as the more modern ones that are using a fountain style of energized particles. That is basically what all time standards are based on. That one, the observatory, U.S. Naval Observatory up in Washington contributes to it, and then there's several around the world that also contributed. I could go on about atomic clocks, and maybe that's a topic for another time. But today we're going to talk about what was on the other side of that campus. And let me go ahead and share. Clicky there, and then that. So you saw the photo of me standing in front of the Space Weather Prediction Center. I've been in a number of different mission controls, and that's kind of how they have their setup. It's a darkened room. There's 2, 3, 4 positions that are sitting there with bunches of monitors. And that's what they're doing all day long and all night long, actually. It's monitored 24/7. They are monitoring a couple of NOAA spacecraft. We'll talk about those. Actually, 2 NOAA spacecraft, and then several different NASA spacecraft. The whole idea is try to understand what's happening with the sun and predict when geomagnetic and other events might be occurring and when they might reach Earth and what impact they might be. So they follow some similar watch and warning type structures, type scales. And it's a shame we couldn't be in person today, because I actually came back with some posters with the different watch and warnings scales and what their descriptions are and why they exist, and some other goodies that NOAA sent along. So maybe next time we get together, I'll be able to bring those and share those with you. But they are part of the Space Weather Prediction Center is part of NOAA, which is part of the Department of Commerce, for a reason. This isn't just about predicting aurora. That's what we're mostly going to be talking about today. I'm sure that's what most of your interest is. And we'll look at some of the products that are here on this website and how to use them. But they exist for safety reasons and for commerce reasons. If you click on the dashboard, and everybody can go here, it's SWPC, as in Space Weather Prediction Center.noaa.gov. Highly recommend you bookmark it. Actually, you'll probably see some dashboards in here that you want to bookmark. This is updated throughout the day. These different dashboards kind of give you an idea of who their main users are, who they're aiming this information at. Electric power grids, when there is a space weather event, when there's a geomagnetic storm that occurs, coronal mass ejection, for instance, that energy's got to go somewhere. And this is a visualization of that. We're in the middle of a G2 moderate storm, and we'll look at the scale in a minute. But there's some goings on, and you can see we're kind of glowing here up in the upper reaches of Canada. This is a joint observation between the US and Canada, in large part because those 2 electrical grids are connected, and the electrical companies cooperate between the US and Canada. And not a geologist, so I don't have a ton of information on this, but I've always found it fascinating how the Appalachians glow. What you're seeing here is the geoelectric field models. So it's basically showing the electrical potential of the Earth. And there's a couple of different observatories. That one dot that's right there, that's outside Fredericksburg, Virginia, not too far from where I went to high school. I had no idea that was there the whole time I lived up there. But it is a observatory that is basically measuring the magnetism of the Earth and the electrical potential of the Earth, particularly the mantle. And I did ask a geologist one time to look at this and give me some idea of what was going on here, why we see the Appalachians glowing like that. And the answer I got was there's a lot of iron content in the rocks that make up the Appalachians, so we tend to see that. But that's just one example of a use case. Here's those fields, and you can see up there around Richmond is glowing for some reason. I don't know why. That's outside of my pay grade. But this is interesting to look at and learn a little bit more. That's just one use case. Emergency management has their own dashboard, and I'll drain a couple of these visualizations that are here and help you understand what you're looking at and what is interesting to what of these are most interesting to see. And you'll see them repeated because they do have use across some different use cases. these geomagnetic events can disrupt radio. So there's a whole dashboard devoted to that. There is a dashboard devoted to satellite operators. Obviously, when there is an event, when there is a coronal mass ejection, when there's billions and billions of tons of charged particles that are being emitted by the sun, as a part of that event, that's going to have some impact on satellites. And it's all, line of sight or line of impact. So if the event, say the CME arrives at Earth at a point where that satellite is, orbited around and is struck, for lack of a better word, it could have some impact. That energy's got to go somewhere else. But there's an interesting impact overall to all satellites, particularly those in low Earth orbit and extremely low Earth orbit. And the ones I'm thinking of in extremely low Earth orbit are our favorite. I'm sure there's some astrophotographers on here that when I say the word, they're going to wrinkle up their faces because these satellites have ruined their pictures many, many times. And that's the Starlink satellites. They are coming out of the sky at a pretty high rate. Let me see if I can find that website real quick. Aerospace, there it is, reentries. So let's look at the reentries. So this is a prediction of upcoming reentries. And just kind of glance through here. And this is just one page of many. And notice how many Starlink satellites are on the page. These are all satellites we're expecting to come down. Those Cosmos ones, I mean, you look at the launch dates on them, they're back in the 80s. You look at the launch dates on some of the other Chinese satellites, and there's a navigational one that's re-entered recently. Those are all quite a while ago. But you look at the Starlinks, and it's 2022, it's 2020. There's one 2023. So these are things that have not been up there very long. The reason they're coming down at a greater rate recently, in large part, has to do with the amount of solar activity that's been going on. We're at a solar maximum. Let me see if I can find that chart real quick. Remind myself where that is. Is it on here? Forgive me, I should know exactly where this is, and I don't know off the top of my head. Space weather prediction center solar maximum sunspot count. So we're in the middle of, so there it is, solar cycle progression. This is what I want. So we're in the middle of solar maximum. Well, we're on the downslope, I should say, of solar maximum. That was declared back in late 2024 that we'd actually reached the maximum. But you can think of the solar cycle as being a bit like a roller coaster. And it's simply a count of the number of sunspots, because that's where all this activity is emanating from, is from really around those sunspots. Sunspots are cooler portions of the surface, as much as the sun has a surface, of the surface of the sun. That's where all of this instability occurs. Instability is a bad thing when you're talking about electrical fields, magnetic fields. When that instability gets great enough, it causes these bursts of energy that come out. But you can see right here that it's kind of all over the place. And for some reason, recently, the main number was way down on the number of sunspots, like way down. Will it nose dive like that forever? Probably not. But you can see that this is kind of all over everywhere. This is an 11-month cycle. Think back to this time last year. Actually, I believe it was the end of May, mid-May, end of May, when we were able to see some aurora here in North Carolina. And actually, the visibility of the aurora went on down to tip of Texas. And I even had some friends that were in the Caribbean that were able to see aurora. This is why we were at that solar maximum. It's the time of the most active points in the sun, again, in this cycle that lasts for 11 years. And there is a very good chance that we could see some additional aurora that far down. So why don't I pause for just a second and see, before I dive into aurora and dive into some of these resources here and how to read them, why don't I pause for a second and see if there's any questions?
Hey, Tony, can you hear me?
Sure can.
So you were just about to tell us why the Starlink satellites come down so frequently.
Oh, I didn't finish my thought there. Yeah, thank you. So during this time of very strong activity, when the sun is, belching out these, tons and tons and tons of charged particles, that causes the outer atmosphere to expand, and it causes it to become more lumpy. We think of the Earth as having an atmosphere, and then there's space, but that's not the way it works. It gets very thin as it gets out farther and farther from the center of the Earth, but it is also not very even. It is even less even during these periods of time where there's lots of solar activity. So that lumpiness is what is causing disruption in the satellites' orbits. And that's bad for satellites. It slows them down, it creates drag, and it causes them to deorbit a little bit faster. Those Starlink satellites really don't have a way to adjust their orbits, unlike, let me bring this up, bring up a visualization. I think they still show this. Actually, I'm not seeing it anymore. This tool that shows you when the ISS is going to be going over next used to show the height of the ISS, and you could see very clearly when, yeah, I guess they don't show that anymore. But used to, you could see very clearly when the ISS would need to be reboosted. All of these low Earth orbit satellites at some point are going to deorbit because of the drag that the atmosphere, the exosphere, the very thin part of the atmosphere up that high, is causing on them. The ISS is low enough that they do have to reboost periodically. Can't do that with the Starlink satellites, so they're coming down more frequently. Now, as this solar activity starts to slow down and it's a little more even up there, we'll see those deorbiting a lot less. And quite frankly, the reason we see so many Starlink satellites is because there's so damn many of them up there. Just the nature of the statistics. Yeah, thank you for reminding me to finish that thought. Other questions? If not, I will move on. So this is the aurora forecast, or aurora dashboard, I should say. So let's talk about these two charts. They're really the same chart, one being tonight's aurora forecast and one being tomorrow night's aurora forecast. The way to read these, there's one for the northern hemisphere, there's one for the southern hemisphere as well. Obviously, we want to see the southern hemisphere. And we're actually fortunate because we have something to look at here since we're in the middle of a G2 geomagnetic storm. I'll just put it out there immediately, and I'm going to pull up my handy dandy chart here that I've got sitting behind me. We need to see at least a G5 geomagnetic storm, and those are pretty rare. The chart that I have in my hand, which is actually available on the SWPC website, talks about the frequency of how often that happens. 4 per solar cycle. So we will, on average, see a G5 geomagnetic storm, which is sufficient enough to get that aurora down to the point where we will see it here in North Carolina, on average 4 times every 11 years. Just to give you an idea. We're in the middle of a G2 right now, which is a moderate, and we see approximately 600 of those per 11-year cycle. That's the way NOAA thinks in terms of how often those happen. Think of it when you hear the phrase like 100-year flood. Same kind of idea. How often do you expect to see those? On average, how often are they spaced out? So what we're looking at here is the aurora forecast. So tonight's aurora forecast. This is a 30-minute forecast. And I'll explain why it's only 30 minutes in a couple of minutes. But the way to read this, that red band has a much higher probability of seeing aurora directly overhead. The green band has less of a likelihood of seeing it directly overhead. Now, the blob there, they call it the forecast oval, that is again pointing to aurora overhead. That is talking about aurora overhead. If you look a little bit below, you see that solid red line that's a bit below the blob. It's labeled over there in the Pacific underneath Alaska. That's the view line. So the view line is also useful, and it's especially useful to us in North Carolina because this is usually what the opportunity that we have to see these. That is the extent of where you might be able to see the aurora low on the northern horizon. And that's happened to us a couple of times. So the way to read this map right here is, those in Michigan, Wisconsin, on down Dakotas, into just the northern part of Iowa. It's worth going out and looking, clouds permitting, of course, for them to go out and look low on the northern horizon, and they might see something. Is it going to be the pretty bands of ribbons of greens and purples and things like that? No. You're much more likely to see that on this map throughout Alaska, in the northern territories of Canada. That's where they're going to see that. What it might look like on our northern horizon, assuming that red line was down by us, is a slight color change, a greening, if you will, of the horizon. But, still worth going out and taking a look. So let me bring up another chart here. So let's think back to I think it was like 2 weeks ago, a week and a half, 2 weeks ago. There was some excitement that we might see a G3 that possibly might move into a G4 severe geomagnetic storm, which would have brought, some possibility of seeing, at least something on the horizon. And it didn't materialize. And I'll show you why. So let's switch from the Aurora dashboard to the Space Weather Enthusiast dashboard. So a couple of things to drain here. We'll start with the chart over on the left-hand side. Don't worry about X-ray flux. Don't worry about proton flux. When those start going wild, that's worthy of excitement. But the charts that you really want to look at, and keep in mind, whenever you see times on here, it's always UTC. It's always Zulu time. It's always universal time. So, do your math and make sure you understand when these things are expected to happen here in the East Coast. But this chart right here is important. This is the KP index. So KP is an abbreviation for a German word that basically means the magnetic potential of the Earth. And these are observations and forecast. So we're forecasting a 6 or greater, which, we're already starting to see some of that. And then it's going to go down to a 5. And then there is expected to be some increased activity, closer to, later this evening, that 5 to the 6, we're already starting to see that. So this is showing what that KP might be like. Now, over on the right-hand side, you'll see that correlated with the geomagnetic storm. It's 2 different numbers, but they're pretty much in lockstep. A KP of 6 is roughly going to produce a G2, a geomagnetic storm level of 2. Again, it's really got to be this dark angry red, a G5, which I believe is a KP of 9, and the scale doesn't go any farther beyond that, farther than a G5 or farther than a KP of 9. It does not go above that. So we basically got to peg that meter in order to see anything here. The other thing to point out here, so got that one. I'll save that one for a little bit later. This is probably the forecast, the text product, if you will, when we're expecting the possibility of some aurora. This is the one that you really want to get familiar with. This is the excuse me, the 3-day geomagnetic forecast, and they put this out 4 times a day. It's very, very similar to the terrestrial weather forecast that the other side of NOAA puts out. Here on the NC State campus is where the Raleigh Weather Bureau is. They put out something for our weather, and they put out storm forecasts. Well, this is put out for all of the United States from the Space Weather Prediction Center in Colorado. The way to read this is those are the 3-hour blocks of time, again, Zulu time, UTC time, and then you get 3 days worth of forecast. The number that is here is the KP, the forecasted planetary index. So again, it's got to be close to a 9 before we're going to see anything really, really spectacular here. And then they got in parentheses what the geomagnetic storm might be. The way to read this, that is what the energy in the upper atmosphere is expected to be at that time. Obviously, when that occurs during our hours of darkness, that's a good thing. We're more likely to see aurora when that happens. Because keep in mind the Earth continues to rotate, and that geomagnetic storm, that coronal mass ejection that's fueling that geomagnetic storm, might arrive at a time when we're turned around facing the sun, so we won't see anything. The ideal time for a geomagnetic storm to arrive is around dusk. The effects of that storm will linger for a couple of hours. If it arrives in the morning, that energy is probably going to dissipate by the time that the sun goes down. We're able to see anything. That's what happened week and a half, 2 weeks ago. The storm was faster arriving. The CME traveled between the Earth and the sun a lot faster than was anticipated. So it hit us about before sunrise. And by the time it got dark here, all that energy had dissipated. The other thing that went sideways for us, kind of literally, and the reason we didn't see anything was that the polarity of those charged particles wasn't favorable. So I'm going to click on this and make it a little bit bigger. There's a lot of information going on here, but the chart that you want to pay attention to, and it looks like we had a little dropout on the ACE spacecraft. This is coming from the ACE spacecraft, which is in Trojan orbit with Earth. It's orbiting roughly on the same plane and path as the Earth, a little bit ahead of Earth. And it is completely a heliophysics mission that's out there measuring the solar wind and trying to help us better understand what the sun is doing. So that red line right there is the BZ line. Right now, the solar wind is trending negative, and that's probably the reason we're seeing a lot of anticipated auroral activity, into the northern United States. It's not strong enough that it's going to make it down to us, but negative is good on this chart. Negative solar wind connects very well with our magnetosphere. And that's what it takes to literally funnel that energy down closer to the equator where we are. You can think of the magnetosphere like a giant donut, Krispy Kreme donut, if you will. The energy is coming in from the top for the northern lights. It's coming in from the bottom for the southern lights. It takes increased energy to push its way down into that donut. If the solar wind arrives or CME arrives and it's very positively charged, it tends not to connect very well with those magnetic fields. So this is another thing to watch. Week and a half ago, when we were anticipating some possible auroral activity, yes, it was strong, but it arrived faster. And these red lines right here were above that dotted line. It was showing very, very positive. So it did not connect very well. Didn't make it down to us. So why don't I pause there and see if there's any questions about the fire hose I just turned on you with some of this data.
Hi there.
Yes. Go, Marshall. That's what I was
Yeah.
going to do. Go.
I put it in the chat, but I'll just ask it. So you mentioned that the time we were expected to be hit by a CME had varied. What causes the time to vary, basically? Like, because for the most part, it's traveling through empty space. And I do know that it doesn't necessarily move at the speed of light.
It absolutely does not move at the speed of light. The radio impacts happen almost instantly. Well, not instantly,
right.
8 minutes away.
Right, yeah.
7 point whatever it is.
So the rest of the particles are affected by something, you know,
They are
what,
physical particles moving through space. Space is not empty. It's
right.
mostly empty, especially closer to the sun. But they are physically moving through space.
So yeah, what like causes those timings, to be so different?
Therein lies the challenge. And that one thing I want you to walk away from here, other than these tools that I'm sharing with you and how to read them and what to pay attention to when we're trying to figure out whether a an event is actually going to produce aurora or not. I want you to have some appreciation for how challenging their job is, how little data they're working with. The sun is the thing in the solar system that we know the least about. We've got a ton of missions out there, and there's a ton of work being done, both academically and within NASA and the other space administrations around the world, to try and better understand the sun, because all of our energy, regardless of what form of energy you want to talk to, it originated in the sun. So this is pretty damn important. But it's the thing we know the least about. Now, take a look at this LASCO image right here. So this is coming from, I believe that's on the Solar Dynamics Observatory. This is an artificial eclipse. It's blocking out the brightest part of the sun so we can watch the corona. Those things that you see there, that's a coronal mass ejection occurring.
Right.
The best we can do is watch that occur and try to estimate its velocity.
Yeah. Okay. That makes more sense.
Yeah.
'Cause
And
it's
we've
like
only been
we're
doing
so
it
affected by that physical, right? Like the physical particles,
yeah.
especially here that we can see in whatever wavelength that
And
is.
as it disperses, it can
Right.
change velocity. So it's a guess. And
Okay.
somebody probably knows the sun Earth distance, to a meter better than I do. But basically, an AU is a long way, and there's a lot that can change in there. So we're getting better at that prediction, but there's still a lot that needs to be done.
Okay. But there isn't like, it almost looks like it's more so the physics that are on, determined by the surface of the sun,
Absolutely.
more so than like anything like in between us and the
100%.
sun that would affect
Yeah.
that.
That's the effect, but how they behave once they leave the sun and are traveling that distance between the Earth and sun has a factor as well.
Yeah.
So I'm
Okay, I
glad
think
that
I mean, it doesn't actually answer my question, but I get it. So
there's not an answer to your
yeah,
question,
right.
unfortunately.
Yeah.
Yeah. And
So
I give that non-answer proudly. That's
all right,
how
well, thank
science
you.
works.
Appreciate it.
Hold on, let me throw a little dog out. Go. Eagle thought he was missing something, so I had to evict him. So I'm glad Lasco is actually showing something here. So you see actually a couple of CMEs that are occurring, and none of these are of any great importance, because the sun, it's easy to forget when we look at all these two-dimensional images, but the sun is very three-dimensional. And when a CME leaves it, doesn't necessarily mean it's coming for us. And the one that occurred week and a half, 2 weeks ago was. So if you look at what's happening with this LASCO image right here, you see kind of the shape of that CME that's coming out of like the two o'clock position. It's kind of round, but not exactly. That's because it's off axis. If it was exactly round and was kind of expanding out towards us, that is what's called Earth directed. And those are the ones we pay particular interest with. Those are the ones that we know that are going to be heading towards us at the very least, and might be aimed sufficiently that they're going to reach Earth. It can take several days for those to reach Earth, and Earth continues to move. So we might move out of the way, and it all depends on the velocity. But those ones that look like a perfect circle, they call them halos. It looks like a smoke ring being blown towards you. Those are the ones that we pay particular attention to. We'll put these others into motion. Now, over on the left-hand side, it's labeled GOES 19, and I think that is actually coming from the GOES 19 satellite, which is a geosynchronous satellite. That's where all of our weather images, all the cloud images we see on the evening news, That's where those are coming from. But there is also, all those cameras are obviously pointed towards Earth. There's also, as of the last couple of GOES spacecraft, they have cameras on board that are pointed back towards the sun, and they're doing some of this heliophysics work. Most of the other images that you see being used by the Space Weather Prediction Center are on the Solar Dynamics Observatory. And you walk into their little mission control, and they've got giant monitors up on the wall with SDO and with GOES. So you see a couple of things going on here with the GOES image, and it also has some SDO images mixed in with it. There's a giant rift down at the bottom. That doesn't necessarily mean that there will be a whole lot of activity there, because if you compare it to the visible light, you don't see any sunspots there. That is absolutely a region that forecasters are going to keep an eye on, and maybe why they're thinking there could be some increased activity, and why you see G2 and G3 forecasted for the next couple of days. So those are the kind of things that they're looking at. Other questions before I move on? All right, I'll show you something else cool. So the WSA prediction here. Can I make this bigger? Yes, sweet. So what you're looking at here is density of the plasma is on top, and the velocity of the plasma. And this is the kind of studies that are going to help us improve those forecasts. It's better understanding, comparing what it looked like when it left the sun, and how long it actually took to get here, and what it was composed of. That's the density part up there. The way to read this, in the middle of those circles, you see that yellow dot. That is the sun. The green dot off to the right, that is Earth. Excuse me, I'm biting a cold. The red dot above it, that is the ACE spacecraft. So, it helps us correlate the data that we're getting. The reason it looks like it's a tennis ball spun and dropped into water and is creating this kind of pinwheel effect is that's the sun's rotation. The sun rotates just like the Earth rotates. And it creates this kind of spray effect with the solar wind that's occurring from it. In different regions of the sun are emitting that solar wind at different rates. And then, of course, the coronal mass ejections. That's what's happening in the pie pieces there. So you can, and again, this is a forecast. You can see as it goes up in time up there at the top. Again, Zulu time, we're talking UTC time. So that coronal mass ejection we saw up in the LASCO image, you can actually see the effects of it there, the predicted effects. The interesting part about this, and the other reason that this is so very challenging, you can kind of see it in this image here. You can see the distance between the Earth and the sun. You can see that, ACE is basically at the same distance as the Earth. It's in pretty much the Earth orbit, or Earth's same orbit. That distance right there is 1 AU. So who can define a Lagrange point for me? Somebody jump in and define a Lagrange point for me.
I think it's the point where the gravity between the Earth and the sun are basically cancel one another out.
It's a wonderful place to put spacecraft because you don't have
Yep.
to use a whole lot of energy to stay there.
Yep.
Who knows what's at L2?
JWST.
The Webb telescope is at L2. It is at L2 because it's a great place to put spacecraft. We can keep it there for a long time without spending a whole lot of energy. It's a nice quiet place. It's a nice cold place, which is great for Webb because her instruments have to operate at extremely cold temperatures to do its infrared job. L1 is where the Discover spacecraft is. So let me bring up Discover. This is a joint NASA-NOAA mission. It's the Deep Space Climate Observatory is what that stands for. And this is just a terrible website. We'll bring up a picture. There's a pretty picture. There's Discover. Is there a better website? Let's bring this up. Where's that pretty picture? Well, this is good. So this is what's aboard Discover. Of course, you have to have your solar arrays to power it. It does have a propulsion module. When you're sitting at one of those Lagrange points, it doesn't mean you're using zero fuel. You're using very little. That's there to keep it in the proper orbit. But it's mostly about the magnetometer that's measuring the magnetic properties of the solar wind that's passing it. That's where we can get the positive and negative. It's measuring the density of that solar wind. There's a number of different missions that are, or I'm sorry, not missions, but instruments that are aboard that are there totally to do in situ science with the solar wind. So if I switch back to the Lagrange points and bring that up, of course, not to scale, but the other images that I showed you of the sun, that LASCO image where we could see this, the coronal mass ejection happening, that GOES image, and in the SDO images, those are just images. That is all of the information that we have between this point right here where the sun is and this L1 point. So the time between the sun and L1, when we're talking about a CMA, is a couple of days. The time between L1 and Earth is 30 minutes, give or take, depending on the speed of the CME. Remember, the first thing we looked at was that forecast map for the aurora. That's why it's a 30-minute forecast. We do not have hands-on, in situ, actually touching the solar wind to measure all these important things about the density, the speed, and most importantly, the polarity until it passes L1, until it passes that Discover spacecraft. So that is why it is so very hard to predict the space weather. And my host, when I was there visiting with the Space Weather Prediction Center, was a gentleman that's in NOAA Corps. So NOAA Corps is a very small officer corps that operates very much like any other military entity, but they report up into NOAA. And he gave me a comparison that I'd like to share with my meteorologist friends because they get it immediately. And they've been frustrated over the last couple of months with, we hear that there might be aurora occurring and then it's a bust. And they appreciate this. They've all been through predicting snow and it's a bust, or how difficult it is to predict hurricanes and their tracks and things like that. So the comparison he gave me that really stuck with me was, picture that you're a meteorologist and your job is to predict when and where and what the impact will be of a hurricane that's forming off the coast of Africa. You have eyes on it. You have a satellite images of it, and you can see it forming and you can see it initially moving. And then you have absolutely nothing until that storm passes a buoy 100 miles off the coast of North Carolina. That's the challenge these folks are up against. Here's your coast of Africa. Here's Earth, and a couple pixels over is that buoy, and that's where Discover is. So that's why this is so very challenging for them. And the fact of the matter is, it's probably going to get better the more experience we get with that kind of forecasting. But this gulf of nowhere to get data. Maybe we can improve some of our imaging here. We can certainly improve our experience on watching these things leaving the sun, but we're always going to have this just total gap of data that's going to make forecasting this pretty difficult. So other questions, what else can I show you here? You're a quiet crowd.
Did we get questions answered in the chat? I see there's some activity that looks like people are responding to that. Maybe Naveen has gone over.
I don't see
And that was
any
the other one.
open
Okay.
questions. in chat.
Yeah, I don't
What
see
was,
any open questions.
Steve Blake put one in chat. Is LASCO a satellite or on Earth? I don't know if that
LASCO is a satellite. Let me remind myself what LASCO instrument. What satellite?
Large angle and spectrometric coronagraph.
It is a coronagraph. Yes, it is. It is on SOHO, the Solar Heliophysics Observatory, and LASCO is fun from an observation point of view because it's pretty rare not to see Mercury in the view. Just where Mercury orbits, you see it often. But here's in big in this. Uh, you can see some stars in there sometimes. This was back in 2000 where Venus just absolutely blows it out because it's so bright. Venus, Jupiter, Saturn, and Mercury are all kind of showing up in the image there.
What wavelength are these images in?
Let me see if they have that listed somewhere. Oh, that's interesting. The shutter time is 19 seconds. So there's
Must be very certainly not visible light then. Or nowhere
Oh
near.
no, absolutely not.
I mean, nowhere near it anyway.
Yeah, I don't know. But
I was
yeah,
wondering if
you're
you knew
absolutely
in
right that
advance.
it's different wavelengths. And you see that in SDO images too. SDO offers just a total variety of
Yeah.
wavelengths, and those numbers are all in angstroms. And this is its magnetometer is or its magnogram is particularly interesting. These are available in pretty high resolution. I say that and then it doesn't want to do it. Let's go daily movies. Look at yesterday's.
What levels or conditions are required to disrupt the power grid?
I'm hesitant to give an answer there because that's not my area of expertise. It's certainly going to be up and closer to the extreme range. That being said, there's a reason there is a dashboard aimed at the power companies because that energy is being introduced into the atmosphere. It's being introduced to the environment, and it's got to go somewhere. So they take measures to protect their equipment. If it's strong enough, there's nothing that they can do. It's just going to take some equipment out. But they are making day-to-day changes in, my understanding is, loads and generation as well, to accommodate the energy that's being introduced into the atmosphere by these events. And I know that's a non-answer, but I'm hesitant to give you a guess there.
Hey, Tony, it's Doug. Just a couple of questions. First one is that are you guys doing anything with measuring the particle density between Earth and Sun?
There's nothing out there.
Well, I mean, isn't there like an intersolar medium, which basically is basically a bunch of just
Yeah,
group that exists between Earth and Sun, and supposedly once you get, it impedes the progress of your first CME, and the second CME basically is not impeded.
There are a number of heliophysics missions out there,
yeah,
that are gathering some data there. When I say there's nothing out there, I'm speaking from a forecasting point of view.
oh yeah,
There's nothing regular out there. But to your point, to better understand the physics of what's happening between L1 and the sun, or between the Earth and the sun, yeah, there's a couple of missions that are out there. That's one thing that the Parker Solar Probe has instruments dedicated to measuring that. And then there was a mission that, and I forget the name of it off the top of my head. We got the first images of the sun's poles recently.
that's my second question, but go ahead.
Yeah, go ahead. You probably know more about it than I do. Go ahead.
No, I don't. That's why I'm asking. But no, I just visually, for us, is there a way? Is there, as we like observe the sun,
Yeah.
from morning until till sunset.
Yeah.
The magnetic pole of the sun actually for us visually here on Earth rotates,
Right.
and do you guys have like any kind of a visualization that we can determine what is north, solar north, at any point in time in the day?
I don't think I understand the question about solar north. Could you phrase it a little differently?
Yeah, no, so like, well, it's when we're usually we have several observing programs that require us to know where the North Pole of the sun is. Um, and so for instance, if I, let's say at 10 a.m. in the morning, it's going to be uh, not too far off of straight up.
Right. Right.
But when we're talking about 4 p.m., it's literally going to be pointing more towards the western horizon. Um, so
This
how
is
do
the
we?
moon's poles change throughout the evening, if I'm understanding you correctly.
Yeah, it's really more of our Earth's rotation versus
Absolutely.
the
Yeah.
sun's our perspective with the sun. And it would be great if there was like maybe a tool that would help us visualize where that's at for any date at any point in time during the day.
Yeah, I
Uh,
don't know off the top of my head. That's a good question.
yeah.
Another resource just came to mind. Let me throw this up here. So you see the current activity out here to the right. That should look familiar. That's the aurora forecast coming straight from NOAA. This is University of Alaska Fairbanks. I use this as a resource, and I point my meteorology friends to it. Um, it's a 3-day forecast of upcoming, uh, possible aurora activity, and it is a good thing to look at in concert with, or in alignment with, the NOAA resources. The NOAA resources tend to be very, very conservative. So when you see this blob here and go, oh, well, there's no way in the world that I'm going to be able to see this, know that they tend to be very, very conservative when it comes to, whether you're going to see aurora or not. Also take a look at this resource at the Geophysical Institute at University of Alaska Fairbanks. It tends to be the opposite direction. It tends to be very optimistic about whether or not aurora might be seen. So let's go to this KP6 that they're forecasting here. On tomorrow evening, and this will actually convert it to Eastern time, which is kind of nice. So they're saying that, and here their solid red line is green. They're saying that if you are, basically around the Manson-Nixon line, that you might be able to see aurora on the horizon. And if you're in the upper Midwest, you got a pretty good chance of seeing it overhead. Whereas you wait 30 minutes before, and take a look at on the NOAA forecast, and this is probably going to be pushed quite a bit forward. Somewhere in the middle probably lies correct forecast. So this is another good resource to look at. And they are also ballsy enough to forecast out 3 days, whereas NOAA is not. And I don't blame them.
Hey, Tony, this is Tony Verdone. I got a question about Starlink satellites. You mentioned them coming down.
Yep.
So if they burn up in the atmosphere, or do they end up in the graveyard in the Pacific Ocean?
These are uncontrolled re-entries. Only controlled entries are able to be directed into that point in the South Pacific that is very, very far from land. So they tend to burn up in the atmosphere. So keep in mind that the Starlink satellites are about the size of the desk most of us are sitting in front of right now. They're not very big. And in the past decade or so, designers of spacecraft in general, and especially anything that's in low Earth orbit, have made efforts to design these things in a way that they will be destroyed upon reentry. So they're just strong enough to do their job, but they're not so strong that they're going to survive all the way to the ground. So they tend to burn up in the upper atmosphere.
We have another question in the chat.
Please.
Is there a connection between solar storms and earthquakes and volcanoes on Earth?
Nope.
Okay.
I don't know how to elaborate on that. Nope.
You probably can't. I mean, so, it's either yes or no, I would think.
Yeah.
Unless the yes had a more detailed, explanation. But if it's no, I don't know if there's any more detail you could do it. So basically they're independent of each other, the solar storms and the earthquakes and volcanoes.
They are, earthquakes are, of course, movement of the seismic plates.
Mm-hmm.
That's happening through forces interior to the earth. And these are all exterior source or exterior influences.
So I did have a question for the CMEs.
Mm-hmm.
Do they also do they measure the neutrinos that are coming? I know neutrinos come from the sun.
Mm-hmm.
Are the neutrinos traveling with the CMEs? Like what sort of particles are with those?
It's a plasma.
That's okay.
Yeah, which by definition is a mixture of particles.
Okay.
Yeah, I don't have a real good answer to the makeup.
Yeah, I thought it would be someone more, something more specific, so that you don't know everything, that's fine. So I was just wondering about that, just to see, just because I know a little bit about neutrinos, but I have no idea how they travel around, so just wondering. Okay.
See if I can find some cool.
Well, the sun is mostly made out of hydrogen, so I assume it's mostly protons, hydrogen nuclei.
That would make sense. Oh, look at this. You can go through and, look at the CME greatest hits over the past 25 years.
Can I buy the CME greatest hits on a CD?
You can give me oh, here's a good halo. Yeah, this one's a little off axis, so I don't know. I have to look back and see. So this is back in 2015. So that was also associated with a couple of solar flares. But yeah, that's a full halo. It's coming right at us. I don't remember how to stop sharing. I don't use Zoom very often.
Well, I don't know. I'm used to WebEx, so I don't find it as intuitive.
It's usually up at the top, Tony.
Yeah.
I got nothing
on screen. I tell you what I'll do.
You take over.
I'll just take over.
That'll work.
Oh yeah, well that would work too.
Well, I thought I'd take over.
How about this? I'll ask the question. What were you hoping to hear that I didn't cover?
Marshall wants you to sell him a CD.
Hey, Tony, this is Steve Arthur. My question really is quasi-political. Are the NOAA and NASA people going to be able to maintain their mission, considering NASA is about to get a cut of 47%?
Yeah, I'm specifically directed to avoid those questions, but I will tell you one story from my visit to the SWPC. So I walk in, the NOAA Corps officer, greets me and gives me the nickel tour, and then we get really deep into discussing, what we're doing here today. Talking about engaging with the public and specifically with what I do with TV meteorologists. How they can better make use of these products and how they can have an influence in their newsrooms and stop people from being disappointed because we've overhyped something that doesn't have a good chance of actually occurring. That's something I feel very strongly about. So we're talking through those kind of things, and trying to come up with some ideas on how we can do better there. Meanwhile, there's a heliophysicist, a forecaster working off to the side, and she's listening to what we're talking about, and she joins in on the conversation. We talk about some like history of past events, and I've still got some papers I need to read that she pointed me to that talk about there's even some ancient like Chinese texts that talk about what we're pretty sure was a CME at the time. Anyway, so I talked to her some more. I find out that she's there on her own. She was one of those employees that was probational at the time.
Yeah.
And I mean, she's got like 3 PhDs and had moved over from one part of NOAA to that part. So technically she was a probationary employee, and she lost her job. But she was there. She still has access to the building for the time. She's not paid, but was there doing research and was showing me the tools she was using to do some of the things that we were talking about before. Taking a known event and going back and looking at, in that case, it was the LASCO images of a CME, and studying how it formed and how it progressed to try and improve their forecast. So when I hear about these budget cuts, I think about people like her. And that's about as political as I will get. But I really, really admire what she was doing there, and her just wanting to stay on the job, and how curious she was, and wanting to contribute to their overall mission.
I guess the other follow-up question would be the commercial folks that depend on this information. I mean, do they contribute at all to its funding, or is it strictly government funding because they need it?
It's strictly government funding, but there is a committee that is set up with consumers of these products, of the forecasts that are coming out of the Space Weather Prediction Center. And there's representation from academia, there's representation from aviation, from the power companies, and they meet, I believe, quarterly and serve as a steering committee to guide the Space Weather Prediction Center and NOAA in general on what kind of information they need, how they want the products to put forth. So I would be surprised if the changes that are happening in NASA and NOAA are not a part of that conversation. So there is some back and forth. But to answer your direct question, no, there is no funding there. Just as, when we go to weather.gov to get the forecast for the weekend to see when we need to cut the grass, well, we don't pay for that either. It's taxpayer funded. Other questions?
Anybody else got anything? So Tony, can I share something with you right before we get off here in case anybody's got a question to interrupt? I want to show you how lucky a human being you are. Are you ready?
Okay.
Do you see my screen?
I can see your screen.
What city is this? Let me give you a hint.
Yeah, I see blackness.
You don't see my screen?
You got to take your lens cap off, dude.
Does anybody else see my screen?
No.
Black. The
Aww.
presentation.
We saw it a second ago, but with the business
we
meeting
go.
coming.
Oh, there we go.
There we go.
Okay.
Yeah, that's that's Boulder.
That's correct.
Those are the
You
flat.
missed me, but I missed you by 1 week.
Really?
You're a lucky man. Anyway.
Yeah,
So for those of you that don't know, he said flat irons.
Yeah,
You'll
they
know
are.
why they say that now.
Yeah, because they're tilted. You can actually see those from Denver if you look close enough.
Yeah.
You were in a park, and I'm trying to think the name of the park. It starts with a CH. Am I correct? Were you in a park
Yeah.
when you took this?
Yeah.
Chapa.
You ready?
Hold on.
Oh, sorry, I already hit it.
Chautauqua?
Yep.
Yeah. Yeah.
Yeah.
Yeah, I hiked that while I was out there.
That's what I'm saying. You missed me by a week.
That park is neat. The adult education outreach, science outreach person in me really appreciates that. Yeah, it's a beautiful place. Absolutely amazing.
I'm sorry. I was trying to show one other thing for everybody, just in case they wanted to. These people were hiking. There's people up here, and it's just as angled as you see it.
Wow.
Yep.
I believe it.
Yeah, that's out of my capabilities.
Yeah, with rock climbing shoes,
that's out
it's
of your
not,
common sense.
it's a
They
little,
don't have ropes on.
yeah, it's precarious, but I could see it.
But that Chautauqua Park is neat because it's got a long history there. It was designed for education.
Yep.
It's a park that's got hiking, but they've got a auditorium there where they don't just occasionally have lectures; they regularly have lectures, and at least monthly by the astronomers at the university there, which I think is really, really cool.
It is. It was very pretty. All right, guys. Any more questions for Tony? All right.
Zoom.
Silent Zoom.
Well, thank you everybody for having me.
Thank you.
for coming.
Hope you got a little something out of it.
Sure
Oh, yeah.
did.
Yeah.
Enjoy
you
that.
Thank you. Thank you very much. You did very well.